afternoon, everyone. So today we have the pleasure of listening to Jalal Fadili from Normandie Université Caen. We'll talk about inertial algorithms with neural network-based methods for inverse problems. Jalal.
Okay, thanks very much, Laure, for the invitation. I'm really pleased to be here. I know some faces. But this is my first time here as a speaker. Okay, I'm gonna try to decipher everything here in the title, and this is joint work with my two former students, Rodrigo and Nathan. Okay, so what's the goal? The goal here is typically to design efficient and probably fast convergence algorithms to solve these kind of problems. So we are in Hilbert space H. We try to minimize the sum of two functions, f and g, and both functions typically are proper, lower sum continuous. F has some extra smoothness, and we have many examples that come from data science, machine learning, statistics, inverse problems, etc. I'm going to go through one application in particular later on. And of course, these problems can be convex or not, smooth or non-smooth, etc. And typically what we're going to do is we're going to transform this minimization problem is in a first order optimality condition or criticality condition, because we don't have convexity here. So typically we're going to say that x star is the solution, meaning it is critical point of the sum of these two functions if it is a zero of some generalized derivative. And this can be a set value mapping. So zero belongs to this guy.
Just to be sure.
Yes.
Okay. H is some kind of Hilbert space.
Yes.
And what's gamma H?
Oh, gamma H, this is the class of proper lower sum continuous functions.
Okay, what?
Lower sum continuous functions.
Okay. And both f and g are in this. Right?
Both f and g.
Why do you split it two functions?
Oh yeah, okay.
You have to explain.
I'm gonna make it even easier later, but typically, okay, here is the typical example. F here is smooth, okay, and this g here can be the indicator function of some constraint set, okay. So in which case, basically, I want to use here the gradient of f, and here I want to use the projector on the B set. So once we have done this, typically, we're going to try to exploit a very old idea between optimization and equilibria of dissipative dynamical systems. So typically, we're going to say that we're going to design some dynamical system which reads in this way. Zero belongs to, so we have this guy here and some function of the derivatives of x. So typically, what I'm going to treat here throughout this talk is we're going to stop at the second order derivative. But for instance, if you have only the first order derivative, this is kind of, and H is the identity. This is something that you all know. It goes back to Cauchy in the 1856 or something like this. This is just the gradient flow. Okay. And typically, these dynamical systems, I'm going to try to design algorithms for this. And these algorithms will be proper discretizations of this type of dynamical systems. Okay. So though I can do everything in a very general setting, so for the sake of simplicity in this talk, I'm going to assume that the non-smooth part is just zero. So I don't have any non-smoothness. Everything is going to be much easier to understand. Okay, where the motivation of all this comes from? So it comes from, in my perspective, from inverse problems. So what are inverse problems? You have an object x bar. So I'm going to even make things even simpler. So my H now is just a finite dimensional Euclidean space. So Rn. And you want to recover something which is close to x bar, but you don't only have access to two things, the observations y, which are indirect measurements of x bar, and the operator f, okay? And possibly with some noise. And you want to invert this system, okay? And you want only to recover x bar or something which is close to x bar under some reasonable assumptions. And you, of course, you want to equip this with mathematical guarantees telling you that what you're going to recover going to be close in some sense to x bar. Okay, in general, the operator f here going to lose some information about x bar, which makes, in fact, the inversion process imposed. For years, what has been really overwhelming in this area, what we call variational models, which are model-based. So typically, what we're going to do is, okay, we're going to cook up a set of candidates to this problem in such a way that if this candidate goes through f, it's going to be close to y. And this closedness, we're going to measure it in terms of L. So L will measure how y is far from fx among all possible candidates x. And which candidates I'm going to promote? I'm going to promote candidates such that these quantities here, these functions of x are small, the smallest possible. For instance, if you know that your solution is positive, here you're going to put the indicator function of the positive orthant, for instance. And if you know that it has small oscillations, you're going to put here some norm with my norm, that would be small when your object has small oscillations, etc., etc. Okay, so what are the pros? The pros of this has been really overwhelming for decades. So it is well understood. It's a minimization problem. We have really deep understanding for everything going on. So we have a wealth of theoretical guarantees in terms of recovery, stability, algorithms, explainability, and interpretability, because we know exactly what the solution looks like. Okay, what are the cons? The cons is, of course, you have to design the RIs. This is not something which is free. Okay, you have to impose some prior. And the choice of this prior is handcrafted. It's the expert who does this. Okay, and it's not always easy. And we're limited, of course, by the set of RIs that we can design. And of course, in a given object, you can have many different structures, and all these structures each structure can be favored by a specific RI here, which makes it complicated to have many different structures within the object X bar. So for instance, imagine I have something like an image, and in this image, I have something which is smooth, but at the same time, I have something with a texture. And texture do not like smoothness, and smoothness does not like texture, because this is oscillating, this does not oscillate. So designing the correct RI that will really favor both is not easy. Okay, so, but this is a criticism that people have been trying really to say about this kind of models. And then we entered the era of database methods. What are database methods? The idea is very simple. Instead of cooking up, handcrafting the RIs, you're going to design an algorithm that will learn these RIs for you from examples of data. Okay? So how we're going to do this? Typically, this is the naive way. Let's say I'm going to put the Y here inside a neural network, and neural network will learn even the inversion process. He doesn't care about the fact that it is smooth, it's not smooth, it's oscillating, blah, 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 about any functional space. It just does the inversion for you, okay? So the engineer will be very, very happy. And the reason behind this is that, okay, if your inverse is reasonable, has some smoothness, and because we know that neural networks have a universal approximation property, so what you hope for is that typically they will learn it correctly, okay? Of course, the engineer does not care about the fact, yeah, the inverse has to be smooth enough, blah, 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 blah. He just puts it and sees if it works. But mathematician would say, okay, it's not going to work all the time, and that's true. And this is what we have to understand. But basically, this is what we're going to do. Instead of doing what I did before, we're going to take a loss here. I'm going to call it L. Now I'm going to take G, which is the neural network. I'm going to feed the output Y, and I'm going to compare the output of the neural network when fed with the Y, and I'm going to compare it to X and see when it's small. So typically, if it learns the inverse, it should be small. And then I'm going to average this among many, many, many examples, okay, to see if it really works. Implicitly, it is learning something, okay? It is learning the inverse. So it is trying to impose some smoothness on the solutions you're looking for. What are the pros? So here, typically, you have off-the-shelf neural network learning frameworks. You don't have to know anything about inverse problems. You just give this to your favorite neural network, and that's it, okay?
Yeah.
Okay. Yeah.
Question, because in the previous problem, you had to choose from the FI.
Yes.
You need to choose the neural network.
Excellent. Yeah, this is what I'm going to say. Okay, no model to think about. Not quite so. Because people will tell you don't have, to choose the RIs. Yeah, but how do I choose this guy? Okay, now look at this. The RIs, I had something like 1, 2, 3, 4. Okay, here I can have billions of parameters, billions of weights. It's even worse. Okay, so don't listen to people who say that, yeah, let the network do it for you, because at the end of the day, you have to cook up what is correct architecture. And this is really not a very easy question. Okay, and of course, you have to train this for all. You have to train it once you have all your examples. Something I didn't say, about the cons here, it is supervised. Meaning what? Meaning I have to have this couple of yi's and xi. Okay, I can do this if I have my phone. I can play around with this, for instance, if I have the blurring problem, something which is easy. However, if I'm in astronomy, for instance, and if I have a telescope, which is, in the sky. And I will have to observe, for instance, the universe, get the yi. I don't know even what the xi is. How do I train this guy? Okay, so for real scientific problems, this kind of things, how to do it, is not that easy. So meaning what? Meaning that you have a price to pay to get the data for training. And this is really very important. Okay, the other thing is, of course, you are learning the inverse, but you are learning one inverse among many. You can have infinitely many even. So now if you take the output of G and you apply your forward operator F, you're not sure that this is going to be close to Y. Meaning what? Meaning that the physics is not really respected eventually. Okay, this is too naive. And of course, people who have been doing this, there were no mathematics. The only paper I know was from 2025, last year, doing this in a very limited setting. But people were really applying this for years now. Okay, then came up another wave saying, okay, we didn't respect the physics in the second. In the first, I have to cook up these functions. Let's try to take the best of both worlds. At the same time, imposing the physics and also learning. Okay, this is what we call hybrid model-based learning. You have many, many of them. I'm not going to go through all of them. I'm going to only focus on one of them later on. But basically, here is the thing is you're going to try to get the best of both worlds. Okay, learn the inverse, but at the same time, respect the physics. And you're going to, account for what we call the forward model. And the prior will be learned either explicitly or implicitly. Okay, with exactly the same question as before, the one you were pointing out is, what is the architecture of my neural network for all this work? And you have to know is that in many, many cases, like for instance, this guy here in Raleigh, you have even to cook up several networks, not only one, but many, many of them. Okay, and and you have some guarantees ensuring that typically that this whole process would not blow up. Yeah, okay. But if you ask someone at the end of the day, when I give you a degraded version of this guy, can you tell me if the output of all these algorithms compares favorably to this guy in a certain sense? No one will be able to answer you. And so far, it's completely an open problem. That's what I'm saying. Okay, so the I choose with yes.
Question. Just a slide before. What IP means from
inverse problems. Sorry, it was too small. Okay, so I'm going to focus on one model here because we did all the math, and another one we're working on, but I will not present it today. Okay, what we call the deep inverse prior. So what is ID? The ID is the following. The idea is to say, okay, now I'm going to take my neural network, and the input of my neural network will be a variable u, and this variable is just drawn at random. And my neural network will behave like a generator. Okay, you've heard about generative AI. It's not exactly generative. It's more like a decoder, but still, it will generate a candidate. And you're gonna take this candidate and you're gonna compare it to Y once it passes through F. And if this guy is small, you're happy. It seems like a very naive idea. When I saw this the first time, I couldn't believe it, because basically, what is the idea behind this? If the set of possible images, which are possible candidates, live on some subset, let's say manifold or whatever, then typically if you take the push forward of mu by your neural network, then this guy that you have here will behave like something which is your original object, X. This is really what's behind generative models. Okay, so this is really naive. And then you're going to optimize theta. So the theta here are the weights of your neural network. So you're going to optimize the weight in such a way that your candidate here, x theta, will be close to y once passes through f. So meaning what? Meaning that here you have a sort of model variety that tells you this is all the possible objects that you can generate. And among all of them, one or several of them will compare favorably to y when they go through f, which makes many, many possible candidates. Okay, and every case parameterized again by the weights. However, you have to do this for each observation. This is what we call a self-supervised approach, meaning, so yeah, I really apologize, but people for machine learning, keep all the time saying this to my students. They keep inventing names for things that exist for centuries. So learning rates for descent step size for gradient descent, for instance, they call this auto-supervised, self-supervised. So, I mean, different names. Even myself, I don't know all of them, but anyway, this is one of the names. So meaning that here you don't have to have a training data set. This is what it means. You don't have a training data set. Okay. In fact, if it works, I'm going to show you that it works. Okay. It means that somehow during the training, something is happening. Okay. Meaning that your training algorithm must induce some bias to push you toward a correct solution, sort of implicit categorization that's happening there. The other thing is, in fact, the Y here, you have noise. And if you put here X theta, which is just the output of a neural network. So typically, yes.
What happened to you in this diagram?
To you, yeah, this is
you.
Yeah. It is in here.
Yeah, but
It's hidden. It's fixed. It's fixed.
yeah, but the minimum is about
That's
with
theta.
respect to theta or
Yeah,
theta
theta.
and you.
No, theta. Only theta. Only the weights.
So where is you?
Yeah, do you, if parameterize this guy, but it is fixed. It's random. Fixed.
It's fixed.
Yeah, it's fixed. Just drawn at random.
So what does drawn at random mean? I mean, what is the
Yeah, I'm gonna show
drawn
you.
referring to what?
Yeah. So this guy will be chosen randomly, typically on the sphere, and once for all.
Once for all per data point, right?
Yeah, for once for all for each Y.
Let
Yes.
me try to understand. I mean, what you're saying is that if you have images,
Yes.
you kind of assume that images can be generated by this super complicated function
Yes.
starting from random.
Yes. Yes.
That's what your assumption is.
Yeah. Exactly.
Okay.
This is what I call the generator.
And this image prior, I mean, this was
Yeah.
now it's archaic in machine learning.
Yeah, it is.
But that's what they were doing. They were just assuming that.
Yeah. They were not saying it like this, but this is precisely what they were doing. Okay. So this is completely unsupervised. It accounts for the fourth model. Very easy. You can ask any student to implement it. It's very easy. However, you don't have, in fact, any theoretical guarantees. I mean, it appears even very naive. And I'm going to show you an example. When I saw this the first time, I was really very surprised. So these are the experiments that we did before analyzing this guy here. So we have Y equal to X bar plus epsilon. And what is the A here? This is a convolution, just a simple convolution. And this convolution, the kernel of the convolution was a low pass. It just cuts off the high frequencies and attenuates the high frequencies and leaves the low frequencies. So typically it was a Gaussian kernel. And then we added some noise. So typically what you observe here is the blurred version of this image. Okay, so after convolving with this kernel, and then adding a lot of noise. So what you are given to the algorithm to the minimization problem I was showing before, and optimizing for the theta, was this guy. And the only thing he knew is Y and A. That's it. And then I run the algorithm. And the algorithm, I'm going to show you what algorithm I run. Okay. And after, let's say, 10,000 iterations, I started seeing this. Okay. No way whatsoever that you will believe that this guy here would come out of this guy, because we only have noise, essentially. Okay. And of course, if I leave it indefinitely, it would have really completely overfit to the noise. I would have observed this guy, so a lot of noise. So this is the reason we stopped it at this iteration. I'm going to give you how we stop in practice. I mean, in theory, even.
So you can solve this with compressed sensing.
Yeah. No. Yeah, of course. It's not compressed sensing, it's convolution. Compressed sensing is just the opposite of convolution. But it's still, yeah, it's a linear inverse problem. You can do it. The only thing is that the X bar that I have here is a very complicated object. It's not like a sparse. Okay. Yes.
The question of Brian is maybe if you had the classical denoising.
It's not denoising, it's an inversion. Yeah.
Restoration problem. Would you have got
Yeah. No, not this quality, but something very comparable. Yes. It would have been explainable. It would have been also a little bit smoother, etc. Yes, absolutely. But the thing is that at this level of SNR, it would have been worse. This is the reason we choose a really very low SNR, very low signal to noise ratio, a lot of noise. So we did it also in another experiment in stereo vision. So typically here, what you have is just restoring an image that you have here from its gradients. So you have this image here. I compute the gradients Okay, and the gradients in this stereo imaging, you can see them as normals to the surface. And then the idea is to reconstruct an image from its gradients, or a singular from a function from its derivative. And the same thing happens. This is the kind of thing that we have after something like 10,000 iterations as well. And here in 3D. Okay. So these were the motivations. Just to explain the algorithm we're using here. So we could have used just gradient descent, of course, but we were not using gradient descent. We did the analysis also for gradient descent. I'm going to present something which is more general, what we call inertial algorithms. Okay. So here is the type of dynamics I was considering here. Don't worry, I'm going to go in detail into this later on. And if you discretize this guy, then you get this type of algorithms. And this is the results I was showing is given by this type of algorithms. Okay, so I'm teasing a little bit here, but this is the kind of results we're going to prove is that we're going to have some recovery guarantees on the outputs. So typically, I will be able to tell you how the outputs, the weights, if you put them in G, it will produce an X, and this X will be close in certain sense to X bar, and how far it's going to be, and what are the parameters that will influence this, okay? And then eventually, I will tell you also, what is the architecture? What is the type for this to work? Because it cannot work for any neural network, okay? There are neural networks for which it's not going to work. So it will solve the problem that we were asking ourselves in the beginning. What is the correct architecture for all this to work? Okay, so in the first part of the talk, I'm going to adopt a completely optimization perspective, and then I'm going to move later on back to inverse problems, because many of the questions we're asking ourselves here are completely optimization, okay? Have nothing to do with neural networks, and then we're going to get back to neural networks afterward. Okay, so I'm going to start with convergence, then what we call trap avoidance. We're going to explain all this, and then I'm going to apply this to the recovery for this neural network type algorithms for inverse problems before concluding. Okay, let's start with convergence. Okay, so the first thing is I'm going to explain you what is kind of dynamics I'm considering. Okay, so recall I consider G to be 0. I'm trying to minimize F. I'm going to assume that F is even C2 and bound from below. Okay, so here if you take the gradient dynamic, so the gradient dynamic basically it searches for direction, which is the steep descent direction. Okay, it's a first order algorithm. But basically, typically what you're trying to do is you have a particle, and this particle, you just leave it to move along the landscape under the sole action of the potential energy. Okay. So this is a possible option. Here, what we're going to do, we're going to try to have better algorithms. What does it mean? Better algorithms, faster ones. And for faster ones, we have to go one order higher. Why? So here we're going to apply another principle of mechanics, okay, which is just the fundamental equation of mechanics, Newton mechanics. So typically you have your particle here, MT, and you can see here your function, the graph your function as your landscape. And here you have your favorite skier who's going downhill and under the action of three forces. So it has a mass, so necessarily the gravity, the reaction of the landscape, and then you have friction. I'm going to neglect here the reaction of the landscape, and I'm going to assume that the particle here has unit mass. Everything is normalized, okay? And if I write here the fundamental equation of mechanics, so typically it just tells me that the acceleration is the sum of the opposite of the forces. And this is precisely what I have here. What you have here is just the friction, and what you have here is just the force that derives from the potential energy, okay? And once you are at equilibrium, if you are at equilibrium at some point, then you are at the critical point of the function f because you are at 0 of the gradient, right? Okay. So now if you look at this type of algorithm, even in the convex case, we can play around with this parameter. I'll leave all these details under the rug, but it's fine. So if you look at the best algorithm you can achieve with this by adjusting this guy here, it has this behavior. So what you have here is fxt as a function of t in blue. And you see it oscillates. You have also here the trajectory because I draw it here in R2. So it oscillates. It's like the pendulum. It's not really something which is surprising from the physical point of view. It overshoots and then it undershoots and then overshoots and then it goes back to equilibrium. So you have this oscillation, and this oscillation is unavoidable with this kind of systems. Okay. However, the envelope is really very good because the envelope, which is the worst case you can do, is really very good, and it is much better than gradient flow. Okay. So can we do even better? And the question is yes, because the natural question is, can I avoid these oscillations? So for instance, can I do something in order to penalize the fact that it is oscillating? So I can penalize, for instance, the gradients themselves. And this is precisely what we're going to do. We're going to introduce an extra parameter here, beta, that will penalize the variations of the gradient, the oscillations. And if you apply the chain rule, this is just the Hessian applied to x dot, to the velocity. Okay, if everything is smooth, blah, blah, blah. So what you have here is just penalization of the, we call this geometric Hessian-driven damping, because we are penalizing the variation of the gradients, and the Hessian appears naturally. Okay, so, and of course, the penalization, you can also introduce it here. I'm not going into details, but this is a very simple idea to understand. For instance, if I had here, this perturbation inside, if I am near the equilibrium, okay, meaning that the velocity is very small, what I can do is just apply Taylor expansion to first order, and if I apply Taylor expansion to first order to this guy, I recover this guy. So these two systems are very close. Okay, here it is explicit, hence the E here, because you see the Hessian appears explicitly, and it is implicit, the I here, because it is inside. So people who are familiar, have you ever heard about Nesterov algorithms? Very popular, machine learning, blah, blah, blah. So this is the physical meaning of Nesterov. Yes.
There is also a classical technique which consists of just stopping artificially the velocity as soon as you climb up, which they call restart method.
Restart, yes.
Do you compare them to the?
Yeah, okay. I can go in a lot of details. This is another PhD for my students. So typically, yeah, you have to play with the gamma here. And to play with this, it amounts basically to adapt it as, so doing, okay, so let's try to answer this formally. In fact, what you're saying, this system that you see here, it is open loop, okay? And the parameters that you have here depends on time, okay? So this system is non-autonomous. Now what you're saying is that I have to make this system even closed loop. I have to make gamma depends on the velocity. Okay, this is much more complicated, but you can do it, yes. But this is not the best strategy. Okay, so for both systems, I'm gonna go through some results. I'm gonna show conversions, global conversions and rates, and also trap avoidance. So what I'm gonna show you is that all these algorithms, even if the problem is non-convex, et cetera, it doesn't matter. Because basically, in most of the time, depending, I mean, if you have a good initialization, it's gonna work, it's gonna go to minimizers instead of going to very bad critical points, what we call supersaddles. Okay. So I'm going to focus only on one of them. For this, I need the notion of Kortikoff-Lorazevich functions. I'm pretty sure many of you know this, but I was not sure. So what is a function that satisfies which is KL function? It is a function that verifies what we call the Kortikoff-Lorazevich inequality. So basically, this inequality, you can look at it analytically, but there's even a better way to understand it, is that the function will become sharp if you reparameterize it. And the reparameterizing function, we call this a desingularizing function. Okay, so typically the function can be flat, and if you reparameterize it by psi, then it becomes sharp. And what you see here is exactly this. You have a gradient growth condition that tells you basically that you're going to grow faster than the objective in terms of gradient if you reparameterize. So the most popular example is the Lorazevich case. So the Lorazevich case is the case where this function is a power function. So the psi here is an increase in a concave function with alpha between 0 and 1. And one which is very popular in the machine learning community is the case where alpha equal to 1/2. Okay. And when this inequality is not local, it's global. Okay. And they gave it another name. They call it now the Polyak-Lorazevich functions. In fact, Polyak has nothing to do with this. Boris Polyak is a mathematician, Russian mathematician. So he's an expert in optimization in particular. But yeah, so they were calling it Polyak, and then people from optimization would say, no, Lorazevich did it before, so they called it Polyak-Lorazevich.
Only Jalal used to say this.
Yeah, myself, yeah. But Jérôme is a very good friend of mine, so I agree with him. Yeah, and this inequality, I'm pretty sure many of you here know this. So this plays a really fundamental role in many areas before, much before machine learning. Going back to optimization, even neural networks, by the way, PDEs, etc. Okay, and what's important here to us is that it allows to derive complexity, so convergence rates. And okay, once you have this is really somehow abstract for the practitioner, and the practitioner will tell you when this will happen. It is a generic property, and if you use some tools from algebraic geometry, and this was actually the whole paper of Cordica, a series of paper by Cordica and also by Ljazovic. In fact, it turns out that there are a lot of functions which verify this inequality. For instance, if you take any real semi-algebraic function, it verifies this. And more generally, what we call tame functions, or functions which are definable on O minimal structures. So typically log x, etc., etc. Only a few functions are not. So we have really to hook up functions who are not critical, which is complicated. And mostly in machine learning as well, most of the functions are KL, yes.
So that we only consider continuously functional function, the KL property.
No. Yeah, because I focus on the case where f is smooth. This is the only reason. Yeah, of course, but I didn't want it to make it too complicated. Yeah, of course, I can make conclusions everywhere, blah, blah, blah.
Can I ask a question?
Yeah, sure, of course.
Is there any example which satisfies this KL inequality for a non-power law?
Here, for non-power law, yes, log x, for instance, or okay, you take L0, for instance. This is a typical example. So, and you have many others. LP, for instance, where P is irrational. So, yeah.
Besides log x, all of them are.
Well, yeah, yes, yeah. But log x is, logistic, for instance, is very popular, and it's not power law. And by the way, don't believe that all convex functions, for instance, if you have a function which is convex, you are done. There was a counterexample in a paper by Jean Bott and his co-authors, where you can cook up a convex function which is not KL. Okay, so let's now look at what happens to this dynamic. For instance, of course, I'm putting on the Dirac existence, but we can prove existence uniqueness of the trajectory, for instance. So if gamma is smooth enough, and if the parameters are well chosen, it cannot work all the time. So meaning what? Meaning gamma has to be chosen in a certain way, beta has to be chosen in a certain way, in this way. Then you have the following. So you know that there is a global solution to this dynamic. And you know also that the velocity, the gradients, everything will be square summable, for instance, here. And what you know also is that the gradients and the velocity will converge to zero. So you're going to converge basically to equilibrium. And not only this, if the function verifies KL, so in particular, if it's definable, then what you know is that the sequence X is even Cauchy. So X, now the velocity is even L1, not only L2, which is really a huge difference. And this will allow you basically to prove that the whole trajectory converges to a critical point. You don't need convexity whatsoever. You only need it to be KL. What about the speed of convergence? Yeah, it has nothing to do here anyway. Okay, so this is the main lesson to learn here, is that in the convex case, the convergence rate will be related to the behavior, the local behavior of your function. So if your function is KL, it has a desingularizing function psi. So the convergence rate of your algorithm, of your trajectory, that you have here, will be related to the desingularizing function. More precisely, it will be given by this very weird function. And the convergence rates are here. So let's have examples, and this is the most important thing. So if here the exponents of what we call the Ljazovic exponent that I showed you before, if it's between 0 and 1/2, then you have exponential convergence. So you converge and exponential. And you have a phase transition, because once you cross the 1/2 to 1, then the convergence rate becomes sublinear, 1/t to some power, okay? And these results were very well known for polynomial functions, for instance. And some algebraic functions are generalizations of polynomial functions. Yes. Yeah, the Q is the exponent of this function psi here is equal to a constant times, so psi t. Okay, so what happens to algorithms? Because in fact, at the end of the day, we discretize everything to implement these algorithms, okay? I'm gonna implement in a very naive way. Why? I'm not going to use very fancy here integrators. It's because I want this to scale up. And to scale up, you have to use something which is not that complicated to implement. So I'm going to use finite differences, only finite differences. Okay, this gives me this algorithm. So what this algorithm does, really intuitively, it starts at xk, at your point, and then it will extrapolate. Okay, it goes in the direction of the velocity. You see here, this is an approximation of the velocity. Extrapolates. And then it takes some risk because it really extrapolates. And then it will go back a little bit. And this is where the oscillations will be attenuated, thanks to the differences of the gradients. See here, nothing depends on the Hessian. And then it applies gradient descent. And it keeps doing this. So, and if you do this way, then everything I've said, don't read this, everything I've said about the continuous dynamic will hold on the discrete dynamic as well, on the discrete algorithm. So meaning I converge to a critical point, and I converge to at a rate which is given by the descent horizon function exactly in the same way. And in particular, the conversion is going to be exponential as before when q is between 0 and 1/2, as before. And it's going to be sublinear if q is between 1/2 and 1, exactly in the same way. Meaning that this discretization here is consistent. So typically, you preserve all the properties of the continuous dynamic. Okay? So what I showed you right now is, okay, I'm going to go converge to a critical point. Am I happy with this? The answer is not really, because what I wanted to do in the beginning, if you remember, I want to minimize a function. If I find a critical point, it might be many, many different points. Okay? Could be even maximizers. Okay? I'm not sure that I'm converging to the correct object here. And what I'm going to show you here is that at least I can ensure that everything will behave in such a way that you're going to converge at least to a local minimizer, if not a global minimizer. Okay? You're going to avoid all bad critical points. Okay. So people have invented a name for this. Not really. I mean, this goes back to many authors in optimization, also in stochastic approximation, try to avoid this. But it turns out that the people who were really interested by that and did all the math were more in the dynamic system community, and goes back even to Poincaré. So yeah, you are converging to a critical point, but the critical point can be something which is even non-critical. I mean, this is non-critical, but this could be a minimizer, maximizer, a strict cell, or flat cell, like this. Okay, and of course, finding global minimum or local minimum, this is an NP-hard problem. Okay, no way to find it. And local descent methods can get trapped into this saddle points, like this one, or even this one, because this is maximizer and I don't want to go maximizer, I want to minimize. Okay, and if this can be avoided, yes. And the answer, for those who are familiar with the Poincaré center stable manifold theorem, this is precisely the idea. Okay, so essentially, what the center stable manifold theorem is that typically the space can be stratified in a way that, in fact, you're going to have a set of measure 1 on which everything will behave well, and in such a way that you're going to converge only to local minima, or at least avoid bad critical points. And if you initialize on the complement of this set, and this set turns out to be measure 0, then you're going to converge to these bad minima. Meaning what? Meaning if I just initialize my algorithm or my dynamical system with stochastically, I mean randomly, with the law which has a density with respect to the bad measure, then I'm done. Okay, because almost surely I'm going to go to good points. So just to give you an intuition of this, in fact, if you look at this function, imagine I have a minimizer here. I think I have a figure I will show you. The only way to go to this guy is to really start at this guy. Otherwise, you're never going to go this. And this self-measure 0, of course. And the same thing here. If you want to go to this guy with the descent algorithm, the only way is to initialize at this parabola, which is right here. And this is again measure 0. Okay. And so I'm going to rule out this case. This case is really the messy one. Okay. So what is this center stable manifold? We're going to say that a point x hat is a strict saddle of a function which is C2, if it is a critical point, and if there is no direction, I mean, if there is, a direction of negative curvature. So this just tells you that you have a direction which is of negative curvature. And we're going to say that function has the strict saddle property if every critical point is either a local minimum or a strict saddle. Meaning what? Meaning I never have this messy case. Okay, because I'm flat here. So if I'm only dealing with functions which are like this, then I'm gonna be in a safe ground. So we can ask ourselves whether there are generic functions that verify this kind of properties. The answer is yes. And it turns out that most functions are strict saddle functions. In particular, these are functions which are C2, and in such a way that at each critical point, the Hessian is non-singular, okay? And it has a countable number of critical points. And these functions are generic, okay? So they're verify the strict saddle property, but also they're the generic in the Bernoulli sense in the space of C2 functions. So this is the type of functions I'm talking about, okay? You see. So here you have only functions where the Hessian is non-singular, and it verifies the strict saddle property. And what I'm going to show you later is if you take this kind of function, it is completely non-convex. It has critical points, which are not necessarily minimizers. But if I initialize here randomly with respect to a measure, which has a density with respect to the Lebesgue measure, then I will never see any bad critical points. I will only go to local minimizers. And here it turns out to be even only global minimizers. And yeah, it turns out that these functions are really nice because not only they are strict saddle functions, but they are also, we can prove it's very easy to prove that they are Loazevich with an exponent, which is 1/2. Not only I will avoid bad critical points, but I'm going to converge to them exponentially because Q is equal to 1/2. Okay, so I only put the, I only put the result for the algorithm. And here is the main result. So my function is C2, okay? It has gradient, which is Lipschitz continuous. And it's definable, meaning that it verifies the KL inequality. Okay. And so if the parameters are well chosen, now I'm gonna initialize my algorithm completely randomly. And the random measure with respect to I'm gonna sample the initialization would have density with respect to the Lebesgue method. Then in this case, almost surely I'm gonna go to a critical point, which is not a strict saddle. And if my function, if it's Morse, for instance, then I know that I'm going to go to a local minimum or a global minimum. Okay? I'm never going to see bad critical points. I'm not going to be stuck into a saddle. Never. Almost surely, of course. So these are the type of functions I'm talking about. So I don't know if you know this type of functions. Are there people familiar with phase retrieval? So phase retrieval is reconstructing an object only from the magnitude of its Fourier transform. Okay, so this is very popular in physics, for instance, and typically this is the kind of function that we encounter. Okay, let's apply this to the deep inverse prior, and then we're going to be done. So yeah, again, we train our algorithm with the the deep prior, as I told you, with this algorithm, and this is exactly the algorithm that I showed you before. Okay, so I'm going to make a few assumptions here, of course, otherwise it's not going to work. And so the loss here is going to be quadratic, just taking the Euclidean norm squared. And here the neural network, if you know how neural networks work, these are just weights, biases, activation. Weights, biases, activation. Weights, biases, activation. This activation, I'm going to call it phi. This function. I'm going to assume that the activation is in my neural network is smooth. Okay. So I'm not going to handle the ReLU, for instance, which is very popular in this area. Okay. But I can handle it at the expense of more technicalities. And I'm going to avoid them here. And by the way, people who do this in machine learning, they don't care about this. They apply all the day, for instance, the chain rule. The chain rule does not apply. Of course, you have non-smoothness everywhere. Okay. So yeah, I'm going to show you basically how the Y behaves, how the X behaves, and eventually I'm going to show you exactly how the network should be designed in such a way that everything works. Okay, let's look at what, yeah.
You assume something on A?
No, here for the moment, no, but I'm going to assume something on A. Yeah, absolutely. But when I'm going to go to X, on Y, I don't need it. Okay, so this guy here, this is the smallest non-zero singular value of A. That's it. Okay, this is not an assumption, just a definition. Okay, don't go through this. Let me explain everything. Okay, train your neural network with this dynamic, meaning with the algorithm that corresponds to this dynamic. It doesn't change anything. Okay? So, and suppose that we have a good initialization. I'm not saying what this initialization is. Okay? So in this community, we call this small initialization. It's a random one, but still. In such a way that if you take this Jacobian of this guy, so here what I'm taking is the neural network, and I'm taking the derivative of the neural network, giving me the Jacobian. I'm going to assume that the Jacobian here is well behaving. Okay, typically the small singular value of this guy is strictly positive. And if I am initializing in a ball which is small enough, then I have the following. First, I have exponential convergence of the loss. So typically this tells you that yt will converge to y, okay, at an exponential rate. And this exponential rate will depend on this product that you have here. And what you see here is actually the conditioning of your problem. If you are familiar with linear problems, this should appear naturally. And this is just the smallest singular value of your help problem, let's say, which is the neural network and the A. So this is fair enough. And at the same time, not only the loss will converge to zero at exponential rates, but also the weights will converge. So the weights, which are the solution of this, the trajectory that you have here, or the iterates, if you have an algorithm, will converge to a global minimizer. A global minimizer. They're not going to strict saddle or whatever. They're going to a global minimizer. They're going to a global minimizer exactly exponentially in the same way. Yes.
But the loss is positive, right? So saying it converges to zero is equivalent to that.
Yes, exactly. Not only it is positive, it has no kernel. So basically here the loss is just norm squared. Yes, exactly. It's exactly as right in this. Okay, and the other thing is now, what I have is, if I stop my algorithm at this iteration, then the difference between the outputs, the observation at time t, and the actual observation, so the x bar that you have here, remember, I wanted to solve in the beginning y equal to ax bar plus epsilon, and this is y bar. This is the perfect observation without noise. What you're expecting is to do at least something which is the order of epsilon. And this is precisely what we have. We are within a precision epsilon. I have noise, of course, I cannot do better. I am within a precision of epsilon around my perfect observation, and I can achieve this exponentially again. This is after time t, which is given by this one bound, which depends logarithmically on the conditioning again. Okay, and this is exactly what we can see. This is a sort of implicit regularization in the sense that we're stopping the algorithm before going to infinity. Because if we go to infinity, we're gonna completely fit to the noise because we're going to zero anyway. So we have to stop before. And people in inverse problems, they call this implicit regularization by early stopping. Okay, so in terms of the object X, now I know how this guy is approached. Okay, the whole guy. Now I want to go from this guy to this guy. And to do this, I have to invert this guy. But I know that I am interested in situations where this guy is not invertible. This is the difficulty. I do not know whether A is invertible. Most of the time, it's not invertible, like in compressed sensing. Okay, so here's what we're going to do. What we're going to do is, I know that I have my neural network. I have theta here, which has been optimized. So U is fixed. The output of G for all the thetas I have here, for all possible thetas, I'm going to call this a model space. This is all so you can just see a neural network like a parameterized function, and the parameters of these functions are theta. Okay, and you're looking at all possible functions that you can produce with your polynomials, for instance. And here it is more complicated than a polynomial. It's a sort of spline, but typically it is this. So, and this is the model space. So this model space I'm represented in here, like this set. And what would be important is I want to recover one object, which is X bar on that set. I don't know whether X bar is even belongs to this guy. I don't know it. Okay, because the design has been made in such a way that I cannot ensure this. But we can approach it. We can approach it by its projection on this set. And what we're going to say is at least A here has to be in such a way that X bar or a good approximation of X bar will avoid the kernel of A. And this is very natural because imagine that X bar was in the kernel of A. What would you observe? Only noise. There's nothing to recover. So the natural assumption is the kernel of A has to avoid some object which is related to X bar. And the correct object, if you're doing this in a Riemannian geometry framework, you will understand it even easier. And this is the reason I'm presenting it here like a Riemannian manifold. This is just the tangent space of your Riemannian manifold at the point you are interested in. And you have to avoid, basically, the kernel of your operator has to avoid the tangent space. Okay, and this is the assumption you were asking me. It's here. A has to be invertible on the tangent space of your model space at the point you are interested in. Natural, very natural. And if this is true, then you have this inequality, which comes from the preceding one, except that I'm inverting everything. So basically, it's a really a two-line inequality. So remember, what I want is I want to go from A, so from YT minus Y bar, and this guy is AXT, and this guy is AX bar. So it means that A XT minus X bar, and I have to invert this A on this guy. This guy lives on sigma. I am translated by X bar. I'm taking, because this is a linear operator, it's a subspace. I have to make everything possibly homogeneous. So I'm taking the conical hole, and the hole is exactly the tangent space. This guy here, everything here, lives on the tangent space of sigma at X bar system. And if this guy is invertible on this tangent space, I can go from this guy to this guy and vice versa. And what I have to pay is the smaller singular value of A on this tangent space. This is what you see here. It's exactly the same quality as before, except that you have here lambda min appearing everywhere. That's it. Okay, again, you have three errors. So this is, restriction injectivity condition. You have three errors. This is the error that comes from optimization, you are training. You have the error that comes from approximation, because this guy can be expressive enough or not to give you exactly X bar or an approximation of X bar. And at the end, you have the noise error. Of course, you don't have a perfect observation. You have an observation that depends on the noise. Okay, so I can give you more quantitative results in the case of compressed sensing in particular, but I'm not gonna do this here. Okay, and you have a trade-off again. This is very important to understand. There is a trade-off between expressivity to have a network which is very expressive, meaning that what? Meaning that this guy has to be the largest possible, but be careful. At the same time, you have to impose this condition. So there is a compromise to have between both. And just a side remark. So I don't know if you're familiar with gradient flow, but if you apply gradient flow, just the minimization of y minus ax squared, and you are solving for x, like a very simple least square problem, this is the kind of convergence rate that you get. And instead, you don't have this one, you have only this one. I don't know if you're familiar with this. It's a sigma a squared that will appear. Okay? When you accelerate, you go from sigma a squared to this one. And we can prove that this is optimal. You cannot improve this one, okay? So here, what you have is the conditioning, and here you have the square root of the conditioning.
We can improve the gradient flow.
Yeah, you can improve the gradient flow that you have here, but eventually what you do it, you can do it for a subclass of functions, conjugate gradient, whatever you want, or you have to modify the algorithm. Yeah, but you can improve it, yes. Okay. So what I told you is, you remember this condition that we're non-degenerate condition where everything has to behave well, blah, 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 blah. So, and this is really the key one. And I have one slide on this at the end. So really you have to be careful about the way you're going to initialize your algorithm. Okay. And in fact, when you look at it, it is very closely related to the literature of dynamical systems, like the Hartman-Grobman theorem. So typically, if you have a dynamical system and you have a hyperbolic critical point, then if you are near that critical point, everything linearizes. And you are like in least squares. So typically, this is the ID. And this is precisely the idea we are using. Okay, and you have also some conservation laws, because I have this smaller singular value of the Jacobian at oscillation. It has to be preserved. And this is really a very important quantity to be conserved. It is a conservation law as well on my dynamical system. Okay. Just to finish on this, you remember this condition? This seems like a weird condition. And we can ask ourselves when this is true. Because, yeah, this is nice. It allows me to do the analysis. It doesn't mean anything from the practical point of view. And in fact, this is instrumental to tell you how the architecture should be cooked up in a way that this is true. Okay? And for this, the key will be what we call overparameterization. So I'm going to consider a neural network like this. This is one hidden layer neural network. So you have the input, you have the weights, the activation, and the output weights. And you're optimizing with respect to V and W. And you're normalizing it properly. We call this the sublinear regime of initialization. The U is uniform on the sphere, and you initialize W like IED Gaussian, and the V here is drawn independently from W and U at 0. And it is really, yeah, it has to have independent boundary entries, and that's it. And if this is true, you have this theorem that tells you the following. So, yeah, to simplify it, it means what? It means the number of neurons, K is the number of neurons in the hidden layer, has to grow like something which is n to the power 2. Okay? It means that the network has to be very wide. We can do the analysis for deep neural networks. I didn't include it here, just to make things more understandable. But typically, it tells you that the neural network has to be really overparameterized for everything to work. Okay? And this is really counterintuitive. People have been thinking for a long time, especially in statistics, and even if you do linear algebra, you have much more unknowns than equations. And it still works. You have much more unknowns than equations. You have n squared unknowns, and you have n equations. Wait.
What you're saying is it's important just for the optimization to start at a good point. It's not because the function has to be complicated that you need a lot of parameters.
Yes, both, actually.
Okay.
But it is true. This is function to be complicated is expressivity, but you have to initialize well as well. You have to have both. And the main lesson, really, I want to convey today is for neural networks, for machine learning in general, what's important is not the minimization problem. What's important is the algorithm you're using to solve your optimization problem. Because this is where everything works. And this is what people have been calling the last years inductive bias, implicit regularization, which are things that are very well known in inverse problems and PDEs. But yeah, you have really to realize what's important is not the optimization problem, is the algorithm. And this is what makes everything work. And you all teach probably how to solve least squares. Then in fact, least squares, even if your matrix has a huge kernel, if you apply gradient descent to this guy, it's going to select one solution for you, which is the minimal L2 norm solution, right? No? Remember this? And this is precisely what happens in practice. Okay, you can have a kernel, but your algorithm will give you only the minimal L2 norm solution. Okay. Yeah, and the same thing will happen also with IGET. I'm almost done. So yeah, just to show you that using this kind of algorithms is better than gradient flow, but I'm gonna leave the slides later on. Yeah, just a few takeaway messages. Inertia is very important to make these algorithms really work, to be faster. Viscous and geometric damping is very important, even for non-convex problems. And we can converge while avoiding bad critical points, what we call trap avoidance. We can have, this has an impact on the recovery guarantees for inverse problems. And also, this will give some keys on how to design the neural networks that are needed for all this to work. And it seems, yeah, at least in experiments that we did, we have really good agreement between what the empirical and the theoretical predictions. So we're working on a lot of generalizations for this, the stochastic setting, the non-smooth setting, the long-time behavior. So to have another look on this, for instance, instead of really being interested by the trajectory with iterates, being interested by the occupation measures of this and for these objects. And typically the natural tool for this is optimal transport. And yeah, we're working also on many other frameworks like the pins. I think there was a colloquium by Georgios Karniadakis.
It's in there.
Yeah, he's right there. Yeah. So this is the father of pins. Okay, other overparameterization regime. Yeah, he's right in front of me. And also about other data-driven methods, I told you we're analyzing much more these days, what we call the plug-and-play and the raw-lane generative models. So these are really very, very, very popular, and we have really to understand them mathematically because they are being deployed in real solutions for medical imaging and for many critical situations. So we have to understand them better. Thanks very much.
Thank you. So there were already many questions during the talk, but maybe we can take more.
In the scheme, you have to calculate the gradient. I'm not familiar with it, but I know it's a challenge in general.
Yes.
And now you're adding the Hessian, which is more complicated.
No, we're never, yeah, this is what I was saying. We never computing the Hessian. What we're computing is the difference of the gradients.
Okay.
Yeah, we never do this because otherwise it would be like having the Newton method and yeah, you have to handle we don't even know how to handle the gradients in general. So this is the reason we are using stochastic methods. But what I did say is that we have generalized all this to the stochastic setting where we don't compute the whole gradient. We compute only the gradient from times stochastic, but we never compute the Hessian whatsoever. Never. Yeah, sorry. No, go ahead.
There's also one question in the chat actually by Luca, but maybe Luca, actually, do you want to unmute yourself and ask the question?
Yeah, can you hear me?
Yeah, sure.
Yes.
Yeah, thank you for the talk. So I'm wondering in your example with the matrix A, what can be said if you only have partial knowledge about this matrix? So for example, a certain structure is known, but not exact values of the entries.
Yes, this is an excellent question. And that would be semi-blind inverse problem. And it is absolutely not within the framework we're dealing with. And it will necessitate other tools. I may have some ideas on how to do it, but this is a completely semi-blind one. So typically, you know, only partly the operator. This is one answer to your question. Another answer would be to say, okay, let's say that now we don't know A, but we know an inexact version of A. So we have some error on A. And what I can do is to try to understand the same guarantees that we did here, but now as a function also of the error that we have on A. You see what I mean? So to capture the error on both A and on Y.
Yeah, you some sort of uncertainty quantification.
Yeah,
maybe.
exactly. Absolutely. Yes.
Okay, thank you.
Thank you.
Are there any other questions?
So in one of the last theorems, you thought you are in a scaling which correspond to the neurotangent kernel.
Yeah.
What about other scalings such as?
Excellent question. Yeah, we can achieve. We are analyzing the paper right now. Okay, what you have to understand is there is a trade-off. There is no free lunch. I can achieve a linear scaling, but at the same time, yeah, there is pretty much private joke, right? So yes, you can have a linear scaling. So typically k greater or equal to something which is constant times n. Yes, of course. But you're going to degrade the rate. You have to pay a price. But you will degrade the rate. The rate will not be the optimal one. Yes.
But because it's also, is it related to also your hypothesis on the initialization?
Yes, absolutely. Yes, absolutely.
So
and we can change this.
Okay.